Welcome to the Deep Dive. Today, we are tackling a really big one, a book that just fundamentally changed everything we thought we knew about life, about history, about us, really.
You mean Charles Darwin's On the Origin of Species, published November 24, 1859, a landmark?
Exactly. And the reaction was just immediate, wasn't it?
Oh, completely. That first edition, something like 12,250 copies, gone. Sold out the very first day. People were, well, desperate to get their hands on it to see what all the fuss was about.
And the full title is quite something, too. On the Origin of Species by Means of Natural Selection, or the Preservation of Favored Races in the Struggle for Life.
It's a mouthful, yeah, but it lays it all out, doesn't it? The whole revolutionary idea is packed right in there.
So our mission today, our deep dive, is to get past the sort of common knowledge and really unpack what made this book such a bombshell. Because, and this is important, the basic idea of evolution, that species change, that wasn't actually brand new, was it?
No, not at all. That's crucial context, really. The idea of transmutation, as they often called it, was kind of floating around. Darwin's own grandfather, Erasmus Darwin, he wrote about it.
And Lamarck, too.
Right. Jean-Baptiste de Lamarck, the French naturalist, he'd put forward a whole theory earlier in the century. You know, species climbing some kind of ladder of life, inheriting traits they acquired.
Like the giraffe stretching its neck.
That's the classic example, yeah. Acquired characteristics being passed on. It seemed logical to some, this idea of striving, but scientifically, it didn't hold up.
So Darwin's genius wasn't spotting evolution, it was figuring out the how.
Precisely. He gave us the mechanism, a practical, observable, non-purposive mechanism, the one he called natural selection.
Okay, so he didn't invent evolution, he invented the explanation for it. That's what we're digging into. The evidence, the idea itself, and the massive philosophical fallout.
Right. And to really get the impact of the origin, you have to start way earlier with the sheer amount of evidence Darwin gathered. Years and years of work before he even, published the theory.
And that came from the famous voyage of the HMS Beagle, right, in the 1830s.
Exactly. 5 years. It was a surveying expedition, but for Darwin, it was this incredible opportunity. He was the ship's naturalist.
So he wasn't just a passenger. He was actively collecting, observing.
Oh, constantly. Collecting specimens, thousands of them, taking incredibly detailed notes, doing geology all over the place. South America, the Galapagos, New Zealand, Australia.
That direct experience must have been transformative, seeing the sheer variety of life firsthand.
Absolutely unparalleled. He got this intimate knowledge of plants, animals, fossils, rock formations, and crucially, while he was on that ship, he was reading specifically Charles Lyell's Principles of Geology.
Ah, Lyell, the geologist who argued the Earth was incredibly old, much older than people thought.
Yes, the champion of uniformitarianism. The idea that the slow, gradual processes we see today, erosion, volcanoes, sediment building up, have been happening at roughly the same rate for, well, basically forever.
Which gives you deep time.
Deep time, exactly. Darwin needed that vast time scale. If the Earth was only, say, 6,000 years old, like Archbishop Usher calculated, his idea of slow, tiny changes adding up over generations just wouldn't work. It couldn't.
So Lyell provided the temporal stage for Darwin's biological drama to play out.
Perfectly put. That geological framework was absolutely essential. Millions and millions of years for natural selection to do its work.
The Beagle voyage also sparked something more personal, didn't it? Something about humans specifically.
Yeah, there's this really striking story. The Beagle had these 3 Phrygian missionaries on board, people from Tierra del Fuego who've been taken to England, educated, and were now being returned home. And Darwin saw them, these sort of civilized individuals, alongside their relatives still living traditionally on the island, whom he privately described in pretty harsh terms like miserable, degraded savages.
Wow. That's a stark contrast.
It was. And seeing that contrast, but also the underlying biological connection, the potential for change, it apparently shattered that old idea for him, the idea that there was this massive, unbridgeable gap between humans and animals.
So it broke down that barrier in his mind.
It seems so. If these people could change so much through education, and if they clearly shared biology with other animals, well, then humans had to be part of the same natural continuum. It paved the way for him to eventually tackle human evolution directly, even though he steered clear of it mostly in the origin.
Okay, so the voyage provides the raw data, the observations, the timescale. But the theory itself, the actual mechanism, that needed another spark, right? And it came from an unlikely source.
It did, not from biology, but from political economy. Thomas Malthus.
Malthus and his essay on the principle of population.
That was the key. Darwin read it in the autumn of 1838, apparently for amusement, but it hit him like a thunderbolt.
What was Malthus's basic point again?
It's fundamentally mathematical. Human populations, if unchecked, grow exponentially 2, 4, 8, 16, while food supplies and resources at best only increase linearly 1, 2, 3, 4.
Meaning you inevitably outstrip your resources.
Exactly. Leading to what Malthus called a constant struggle for subsistence. Competition, famine, disease. These things keep the population in check. It was a pretty bleak outlook on social reform, actually.
But Darwin saw something else in it.
He made this brilliant leap. He realized the struggle wasn't just a human thing, it applied everywhere. To plants, to animals. All organisms produce way more offspring than can possibly survive. Think of fish eggs or seeds from a tree.
Millions are produced, but only a few survive to reproduce themselves.
Right. So Darwin connected Malthus's population principle to his own observations of variation within species. He saw that individuals aren't identical clones, they vary.
Some are faster, some are better camouflaged, some resist drought better.
Exactly. And in that constant, inescapable Malthusian struggle for existence, if individuals vary and if those variations affect their ability to survive and reproduce.
Then the ones with the slightly helpful variations would have an edge.
Precisely. He wrote it at once struck me. Favorable variations would tend to be preserved, passed on to the next generation, while unfavorable ones would be, well, destroyed or weeded out.
And over time.
Over enough time, the accumulation of these favorable variations would lead to populations changing, adapting, potentially becoming new species.
Wow, so Malthus provided the concept of the struggle, and Darwin combined it with variation and inheritance.
He said he had at last got a theory by which to work. It was simple, logical, almost brutal, but it explained so much.
Okay, let's break down that mechanism, natural selection, a bit more formally, because it's often misunderstood. Ernst Mayer's summary is really helpful here, separating the facts from the inferences.
Yeah, Mayer has laid it out beautifully. It starts with 4 observable facts, things Darwin saw everywhere.
Okay, fact 1.
Fecundity. Basically, organisms make way more babies, or seeds, or spores than could ever survive. Potential for exponential growth.
Fact 2.
Population stability. Despite that potential, populations in nature tend to stay roughly the same size over long periods, so clearly most offspring don't make it.
Fact 3.
Individual variation. Look around at any group of animals or plants, they're not identical. There's natural variation in almost every trait. Size, color, speed, whatever.
And critically, fact 4.
Heritability. A lot of that variation is passed down from parents to offspring. Tall parents tend to have tall offspring, for example.
Okay, so those are the facts. Overproduction, limited survival, variation, and heritability. Pretty undeniable stuff.
Right. And from those 4 facts, 2 key inferences logically follow.
Inference 1.
The struggle for survival. Since more are born than can survive, there must be intense competition for resources, mates, avoiding predators, a constant struggle.
And inference 2, the core of the mechanism.
Differential success. In that struggle, individuals with inherited traits that give them even a tiny advantage in their specific environment are slightly more likely to survive and reproduce than others.
And because those traits are heritable.
They pass them on. Over generations, those advantageous traits become more common in the population. The population adapts. That's natural selection.
He called it a process of preservation and discarding, didn't he?
Yes. What's useful in a given environment gets preserved, amplified. What's useless or harmful gets discarded, eliminated.
And the key is that utility is defined purely by the environment, by the conditions of life. There's no goal, no direction, no mind behind it.
Absolutely none. It's a blind, automatic process. Utility over long periods. That's the revolutionary, and for many, the disturbing part.
Which brings us right to why this book caused such an immense philosophical shockwave. It wasn't just about challenging religious creation stories, was it? It went much deeper.
Much deeper. Darwin was fundamentally attacking a way of thinking that had dominated Western thought for, well, over 2,000 years. This idea called essentialism.
Essentialism, meaning?
Meaning that the true reality of things lies in their fixed, unchanging essence or form. Think Plato's forms or Aristotle's ideas about species having a perfect blueprint. Change, variation, flux sanctions, those were seen as imperfections, deviations from the true ideal type.
So when people look at, say, a species of bird, they saw it as fulfilling a preordained perfect pattern.
Exactly. The Greeks used the word eidos, meaning form or idea. Later, the scholastics translated it as species. Each species represented a fixed, perfect telos, and individual variations were just noise, unimportant accidents around that perfect essence.
The whole world was seen as designed around these fixed blueprints.
Right, and Darwin comes along and says, no, those fixed forms aren't real in that sense. They're just temporary snapshots in a constantly changing process. The variation, the aimless flux, that's not noise, that's the raw material that selection works on. The reality is the change.
Wow, that completely flips the script. It undermines the very logic people used to understand not just biology, but everything morals, politics.
Everything based on fixed, eternal truths. If species aren't fixed, maybe human nature isn't fixed. Maybe moral laws aren't fixed. You can see why it was so explosive.
And while the public debate often got framed as science versus religion, you're saying Darwin saw the core battle elsewhere.
Yes, the sources suggest he felt the real intellectual battle was within science and philosophy, challenging that deep-seated essentialism. He apparently wasn't that bothered by the theological clamor, as one source puts it, except maybe how it upset his wife and daughters.
So who did he need to convince?
His benchmark for success was winning over the scientific establishment. Specifically, three key figures: Charles Lyell, the geologist, Joseph Hooker, the botanist, and Thomas Huxley, the zoologist, who became known as Darwin's bulldog.
If he could get them on board with evolution by natural selection, he figured the rest would follow.
Pretty much. Convince them that change was real and selection was the engine, and the old philosophical framework would crumble.
And the biggest pillar of that old framework was the argument from design, wasn't it?
Absolutely central. Before Darwin, it was almost intellectually watertight. People looked at the incredible complexity and adaptation in nature. The eye, a bird's wing, a flower's structure.
And concluded, it must have been designed by an intelligent creator. William Paley's watchmaker analogy.
Paley's argument was hugely influential. Find a watch on a heath, you know it had a maker because it's complex and purposeful. Look at the eye, even more complex and purposeful, therefore. It must have a divine watchmaker. Adaptation proves God's existence and benevolence.
And natural selection just pulls the rug out from under that.
Completely. Darwin showed how you could get that same complexity, that same exquisite adaptation without a designer. All you need is random heritable variation and a filter the struggle for existence that automatically presumes the variations that happen to work better.
So adaptation becomes an automatic consequence of the process, not evidence of prior intent.
Exactly. It eliminates the need for that prior intelligent causal force. But we should add, Darwin himself still felt a sense of awe. He wrote privately about finding it impossible to conceive this immense and wonderful universe as the result of blind chance or necessity.
But personally feeling that awe is different from making a scientific argument.
Right. Scientifically, he argued, since variation occurs in all directions, useful and useless, you couldn't justify the design argument. The mechanism of selection acting on random variation was enough. Blind, maybe, but sufficient.
Okay, let's dive into the book itself. Origin is known for being incredibly persuasive. How did Darwin structure his argument to win people over?
Well, he starts very cleverly, not with fossils or abstract theory, but with something familiar to everyone in Victorian England. Breeding. Chapter 1 is all about artificial selection. Pigeons, exactly. He talks about the incredible variety of domestic pigeon breeds, pouters, tumblers, fantails, and points out that they all descended from one wild ancestor, the rock dove.
So he's showing the power of selection when guided by humans. Look what we can do in just a few generations.
Precisely. If humans, by picking the traits they like, can create such diversity relatively quickly, imagine what nature, selecting for survival over millions of years, could do.
It's an analogy. He then argues the line between a variety, like a pigeon breed, and a distinct species is kind of fuzzy.
Yeah, he says a well-marked variety may be justly called an incipient species, an early stage of a new species forming. Nature's selection is just slower, more rigorous, and acts on traits useful for survival, not just looks.
But you mentioned he made a mistake right at the beginning of that chapter. Something about why domestic animals vary so much.
Yes, it's a fascinating little detail. In the opening sentences, he suggests domestic animals are more variable because their conditions of life, food, shelter are less uniform, and maybe a bit cushier than in the wild. He thought the environment somehow induced more variation.
But that's not quite right, is it?
No. We now know variation arises randomly through mutation. The reason domestic animals show more variation is because natural selection isn't weeding out the extremes as harshly. Breeders actively preserve weird traits, like a fantail's tail that would get a wild bird killed pretty quickly.
So natural selection normally stabilizes things, removes the oddballs, whereas artificial selection can let them flourish. Darwin sort of had it backwards initially.
He attributed the cause incorrectly, yeah. He didn't understand the source of variation, which is a huge challenge for him throughout.
Speaking of challenges, he knew his theory would face major objections. He tackles them head on in the book. What are the big ones?
Well, the first massive one was the fossil record, or rather, the lack of intermediates in it. If evolution happens through tiny, gradual steps, shouldn't we find countless transitional fossils linking different species?
And mostly we didn't, or at least hadn't then. How did he counter that?
He relied heavily on his friend Lyell's arguments about geology. He argued the fossil record is incredibly, profoundly imperfect. Fossilization is rare, huge chunks of geological time are missing, erosion destroys evidence. It's like having only a few randomly saved pages from a massive, multi-volume history book.
So the gaps are expected, not evidence against the theory.
That was his argument. Plus, he suggested that new species might often arise in small, isolated areas and then spread rapidly, making their appearance in the wider fossil record look sudden, even if the process was gradual locally.
Okay, what about complex organs? The eye is the classic example. Critics said, what good is half an eye? How could something so intricate evolve step by step if the intermediate stages weren't useful?
That was a huge one. Darwin admitted, if it could be demonstrated that any complex organ existed, which could not possibly have been formed by numerous successive, slight modifications, my theory would absolutely break down. He knew it was critical.
So how did he defend it?
He used comparative anatomy. He pointed to existing animals that show a whole range of light-sensing organs, from simple pigment spots in invertebrates right up to complex camera eyes like ours.
Showing a plausible pathway.
Exactly. Even a simple light-sensitive spot gives some advantage over being blind. A slightly better ability to detect light direction is better than just detecting light. Each tiny improvement could be favored by selection. You don't need the final perfect eye from the start, you just need each step to be slightly better than the last.
He also tackled instincts, didn't he? Complex behaviors like bees building hexagonal cells or ants making slaves. Those seemed hard to explain by gradual change.
Yeah, Chapter 7. Things that looked like perfect, pre-programmed designs. Darwin argued these weren't special creations, but arose through the same process. Natural selection could favor slight variations in instinctual behavior.
How so? Like a bee that happened to build slightly more efficient cells.
Right. If a bee lineage had a slight variation that let them build strong cells using a tiny bit less wax, that colony might be more successful, waste fewer resources, and raise more offspring, including new queens carrying that slightly better instinct. Over time, the instinct gets refined. It's all small consequences of one general law, as he put it.
But there was one problem he called his most serious special difficulty. It wasn't organs or fossils, but insects again.
Sterile insects. Specifically, the workers in social insect colonies like ants or bees.
Why were they such a problem?
Because they're sterile. Natural selection works because individuals with advantageous traits reproduce more, passing those traits on. But worker ants often have highly specialized bodies and instincts, yet they don't reproduce. So how could those traits evolve and be passed down? A beneficial mutation in a sterile worker should just die with her.
Ah, right. If they can't pass it on, selection can't act on it directly. How did he solve that?
It was ingenious, actually. He proposed that selection could act at the level of the family or the community.
Not the individual.
Not the sterile individual, no. Think of an ant colony. If some colonies happen to produce sterile workers that are slightly better defenders or foragers or nurses, that entire colony will be more successful. It will thrive and produce more reproductive individuals, queens and males, than other colonies.
So the traits of the sterile workers benefit the reproduction of their relatives, the queen mainly.
Exactly. It's selection acting on the family unit because of the useful traits expressed by its sterile members. It was an early glimpse of what we now call kin selection, a brilliant solution.
But underlying all these specific problems was the big one you mentioned earlier, the heredity headache. He just didn't know how traits were passed on.
He admitted it point blank. The laws governing inheritance are quite unknown, and this lack of knowledge left a huge gap, which his critics exploited.
This leads to Fleming Jenkins' critique, right? The blending problem.
Yes. Jenkin, a Scottish engineer, pointed out in 1867 that under the commonly accepted idea of inheritance at the time, blending inheritance, Darwin's theory seemed impossible.
Blending, meaning offspring, are just an average of their parents. Like mixing black and white paint gives you gray paint.
Precisely. And Jenkin argued, quite logically, that if a single individual popped up with a new advantageous trait, when it mated with ordinary individuals, that advantage would be blended, diluted, halved in the next generation, quartered in the one after. It would just wash out into the population average very quickly.
It wouldn't be able to accumulate over time like Darwin needed.
Mathematically, based on blending, Jenkin was right. It was a powerful critique. It really troubled Darwin.
Did he try to address it?
He did. In 1868, he proposed his own theory of heredity, a provisional hypothesis he called pangenesis.
Pangenesis. What was the idea?
It was, well, a bit strange. He suggested that all parts of the body, liver, brain, muscles, everything, constantly shed tiny, invisible particles called gemmules. These gemmules supposedly traveled through the bloodstream and collected in the reproductive organs.
So the sperm and eggs would contain a mix of gemmules representing the entire parent body.
That was the idea. But the problem was, this model accidentally made room for Lamarckian inheritance again. If you, say, strengthened your muscles through exercise, your muscle gemmules might change, and you could pass on stronger muscles directly.
So it allowed for the inheritance of acquired characteristics, which undermined his main mechanism of selection on random variation.
Exactly. In trying to solve the blending problem without knowing about genes, he inadvertently weakened his core argument. It shows how critical that missing piece of the puzzle genetics really was.
Okay, so the theory itself started to evolve, even the language used. And Darwin's contemporary, Alfred Russel Wallace, played a role here.
He did. Wallace, who independently came up with the idea of natural selection around the same time, actually urged Darwin to drop the term natural selection.
Really? Why?
Wallace felt it was a stumbling block. He thought personifying nature as selecting traits confused people. It made it sound like there was a conscious chooser, like a human breeder, which wasn't the point at all.
So what did Wallace suggest instead?
He preferred a phrase coined by the philosopher Herbert Spencer in 1864, survival of the fittest. Wallace thought that was just a plain, straightforward description of the outcome the fittest survive. No agency implied.
Yeah, Darwin did adopt that phrase, didn't he?
He did, partially. He added survival of the fittest to the 5th edition of Origin in 1869. He called it more accurate and sometimes equally convenient. But he never fully abandoned natural selection. He kind of hoped people would eventually get what he meant by it. He even said if he were starting over, he might have used natural preservation.
Interesting. But despite Darwin's success in initially convincing many scientists, you mentioned earlier that natural selection actually lost favor for a while after his death.
Yeah, it's quite remarkable. From about the 1880s up to the 1930s or so, there was this period often called the eclipse of Darwinism.
An eclipse, meaning most scientists accepted evolution, but not necessarily Darwin's mechanism for it.
Exactly. Evolution as a fact was largely accepted, but natural selection seemed too random, too undirected, too brutal for many. And Jenkins' blending critique still cast a long shadow.
So what other mechanisms did they prefer during this eclipse?
Several alternatives gained traction. Things like orthogenesis, the idea that evolution has an inherent built-in drive towards complexity or perfection, regardless of selection. Or neo-Lamarckism gained popularity. Again, the idea that acquired traits could be inherited, offering a more purposeful-seeming way for organisms to adapt.
These alternatives seem to offer more order or direction than blind selection.
They did. They satisfied a kind of philosophical preference for progress and purpose that Darwin's mechanism lacked.
So what brought natural selection back from the shadows? What ended the eclipse?
The solution to the blending problem. It came with the rediscovery around 1900 of Gregor Mendel's work on genetics.
Mendel and his peas.
Mendel and his peas, yes. He'd done his experiments decades earlier, showing that traits are passed down by discrete units, what we now call genes. Inheritance wasn't like mixing paint, it was particulate. Traits could be hidden for a generation, but reappear later unchanged.
So no blending. Jenkins' critique was based on a false premise about how heredity worked.
Precisely. Mendel's particulate inheritance provided the missing piece Darwin needed. It showed exactly how variation could be preserved and passed down generation after generation, allowing selection to work gradually over long periods.
And this led to the modern synthesis.
Yes, in the 1930s and 40s, scientists like Ronald Fisher, J.B.S. Haldane, Sewell Wright, Theodosius Dobzhansky, Ernst Mayr, they brought together Darwin's selection, Mendelian genetics, population statistics, paleontology, everything. They forged a unified theory of evolution often called neo-Darwinism.
So Darwinism wasn't replaced, it was synthesized with genetics.
Right. Selection acting on genetic variation became the undisputed core mechanism of evolution again, and has been ever since.
Now, before that synthesis, going back to Darwin himself, he famously avoided talking much about humans in the origin, didn't he?
He did, very deliberately. He knew it was the most controversial aspect. He apparently told a friend he wanted to avoid the whole subject, as so surrounded with prejudices.
But he left a little hint.
Just one tantalizing sentence near the end. Light will be thrown on the origin of man and his history. He knew perfectly well what that implied.
And he did eventually tackle it head-on in The Descent of Man in 1871. How did he apply his ideas there?
He argued that humans evolved from earlier ape-like ancestors, applying both natural selection and, quite heavily, sexual selection, the idea that competition for mates drives the evolution of certain traits.
But the sources mention that his arguments in Descent sometimes reflected the biases of his time.
Yes, unfortunately. While groundbreaking, his discussions on human races and the differences between sexes often drew conclusions that seemed to provide a naturalistic basis for the social hierarchies and prejudices of the Victorian era. For instance, suggesting male superiority in intellect or strength was partly a result of sexual selection and the struggle for life.
So his scientific theories became entangled with prevailing social attitudes, which later fueled things like social Darwinism.
Regrettably, yes. The application of evolutionary ideas to human society has a complex and often troubling history that started right there with some of Darwin's own speculations in Descent of Man.
Okay, let's bring it to the present day. Why is Darwin still so fundamental? One powerful example is seeing his mechanism work right now in our lifetimes. Antibiotic resistance.
It's the perfect textbook example of natural selection in action. Fast, visible, and with huge consequences for us. It demonstrates all of Darwin's core principles.
So walk us through it using Darwin's logic.
Okay. First, you have a massive population of bacteria. Within that population, there's random variation due to mutations. Most bacteria might be susceptible to a particular antibiotic, but just by chance, a few might have a mutation that makes them slightly resistant. That's variation and heritability. The resistance gene is passed on.
Then we introduce the struggle for existence.
Exactly. We apply the antibiotic. That's the selective pressure, the environmental filter.
What happens?
The antibiotic kills off, discards the vast majority of susceptible bacteria. But the rare individuals with the resistance mutation survive. That's differential survival the fittest in this specific context.
And because they survive, they reproduce.
They reproduce, passing on their resistance genes. Since most of their competitors are gone, they proliferate rapidly. Pretty soon, the entire bacterial population is dominated by the resistant strain.
Preservation of the favored type, driven by the environment we created. It's Darwin 101, happening in hospitals and on farms everywhere.
Precisely, a direct, observable confirmation of his mechanism.
And witnessing that mechanism confirms the deeper philosophical point, doesn't it? That biology, at its root, seems to be mechanistic.
It really reinforces that shift away from purpose and design towards a view of life driven by understandable material processes. Blind variation, environmental filtering.
What are the big philosophical consequences of fully embracing that mechanistic view, according to the sources?
Well, one major implication is that it challenges the idea of inherent fixed moral laws handed down from on high. If we're products of evolution, our moral systems are likely evolved behavioral strategies that helped our ancestors survive and cooperate in groups.
So morality isn't absolute, it's adaptive. It reflects what works for group survival in a particular context.
That's the implication. Our sense of right and wrong might be a product of our evolutionary history, shaped by the need for social cohesion, rather than reflecting some eternal objective truth. If the environment or social needs change, the moral rules might also shift over time to remain adaptive.
That's a profound challenge to traditional ethics.
It is. And another deeply challenging implication, for many, relates to free will.
If everything is mechanistic, driven by genes and environment, where does free choice come in?
The strict mechanistic view suggests that what we experience as free choice is actually the outcome of incredibly complex but ultimately deterministic processes in our brains. Our decisions are the result of our genetic predispositions interacting with our lifetime of experiences and the immediate environmental triggers.
So we're complex biological machines, making choices based on our programming and inputs, rather than some independent self standing outside the causal chain.
That's the unsettling conclusion many draw from a purely mechanistic post-Darwinian worldview. No ghost in the machine, just the machine itself operating according to physical laws.
It seems like some of the core debates from Darwin's time are still with us, just maybe phrased differently.
Definitely. Think about the pace of evolution. Darwin emphasized gradual, slow change, gradualism. But even some of his supporters, like Huxley, thought maybe bigger jumps or saltations were needed sometimes.
And that debate about gradual versus jumpy change continues.
Absolutely. It's echoed today in discussions about things like punctuated equilibria, the idea proposed by Niles Eldredge and Stephen Jay Gould. They argued the fossil record mostly shows long periods of stasis species staying the same, punctuated by relatively brief bursts of rapid change and speciation, especially in isolated groups.
So long periods of boredom interrupted by moments of excitement versus constant slow change.
Kind of, yeah. It's a debate about the tempo and mode of evolution. Most biologists agree natural selection is the main driver, but they still debate whether change is mostly slow and steady, neo-Darwinian gradualism, or happens more in fits and starts, punctuated equilibria. The fundamental questions about how change happens persist.
So summing up, Darwin's incredible achievement was twofold: convincing the world evolution was a fact, and proposing a workable mechanism, natural selection, which, after its eclipse, became central again thanks to genetics.
Yes, he provided the unifying framework for all of biology, a framework that explains life's incredible diversity and complexity through natural processes without needing recourse to supernatural design.
And he ends the origin with that beautiful, famous passage about the entangled bank.
It's a stunning piece of writing, picturing a riverbank teeming with diverse life plants, birds, insects, worms, and reflecting
That these elaborately constructed forms, so different from each other and dependent on each other in so complex a manner, have all been produced by laws acting around us.
And then that final sentence, which in later editions included a nod to a creator, possibly to appease critics or perhaps reflecting his own complex feelings.
There is grandeur in this view of life, with its several powers, having been originally breathed by the Creator into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved.
Grandeur indeed. Whether you include the initial breathing or not, the core idea is this vast, unfolding tapestry of life from a simple origin driven by natural laws.
So for a final thought, let's consider that idea from the philosopher John Dewey you mentioned earlier, that progress sometimes comes from just abandoning old questions we can't solve rather than answering them.
Right. Dewey suggested we don't solve certain problems, we get over them. Darwin's revolution, in a way, forced biology to get over the question of design versus chance by providing a mechanistic explanation that made the old framing obsolete.
So the provocative question for you, the listener, is this: if the design debate was a question the 19th century had to abandon to move forward, what deeply ingrained, seemingly insoluble question are we grappling with today, maybe in science, maybe in society, maybe personally, that we might need to just get over? What question might disappear if we fully embrace the kind of process-oriented, mechanistic logic that Darwin unleashed?
Something to think about as you observe your own tangled bank, whatever that might be.